Great.
Okay, so the next part is Latent-Variable Synchronous CFGs for Hierarchical translation. And the first author is going to present, Avneesh. Please start.
Thanks, Khalil. Good afternoon, everyone. Yes, today I'm here to talk to you about latent variable models for synchronous grammars and translation. And this is joint work with my advisor, Dyer at Carnegie Mellon and Shay Cohen at the University of Edinburgh. All right, so say we want to translate the following sentence from German to English. Diese Fragen werden Ihnen mehr nach Katzen fragen lassen. And for those of you who don't know German, here's the following translation. You'll automatically notice, or you'll immediately notice that Fragen can translate to both questions and to ask. So clearly, just relying on word or lexical-based translation is not going to get us very far in terms of disambiguating these two translation options. This has been the main motivation when going from words to phrases in previous work in translation. In this particular case, we find that these doesn't occur with the verbal form of Fragen, so we can conclude that diese Fragen means these questions. So this is one way of disambiguating. Of course, these rules can be hierarchical or gappy as well, as with Hiero, and they can also incorporate syntactic information. So in this work, we're going to actually look at we're going to restrict ourselves to Hiero, but a lot of the ideas can be also looked at in syntactic translation. So the basic idea, in other words, for disambiguating translation options is to stuff more information in the form of local context inside these translation rules. So we come up with these larger translation rules, which result in larger models, and this has both computational and statistical issues. The basic assumption, thus, in previous work is that in order to get contextually richer translation models, we need these larger, more rules, and that's going to come up with these larger models. And so that's actually, that observation is encapsulated in the result, in previous results that show that composed grammars, namely grammars that consist of rules which can be decomposed into smaller rules also existing in the grammar, or correspondingly, when rules are basically formed from smaller rules by combining them to generate larger rules, the observation that composed grammars tend to do better than minimal grammars. So what I mean by minimal grammar is that during the phrase extraction process, for every word-aligned sentence pair, we extract the consistent rules, and also those rules cannot be decomposed further into smaller rules that also explain that sentence pair. In this particular example, we see diese Fragen together. And obviously, this does better, as we've seen in previous work, but what has this led to? So in this particular case, we ran some experiments, or these are some real numbers. We see that a composed grammar, namely, say, Hiero or something along those lines, is 40 times larger than a corresponding minimal grammar, and that means it's harder to index. You have to prune, you have to do some kind of beam search and whatnot. And so the question is, can we get the best of both worlds? Can we somehow keep our grammars small, but incorporate context through some other ways? And the idea is, how about modeling context through latent variable models? And this idea isn't as crazy as it sounds. There's a definite precedent in the monolingual parsing literature. The late 90s saw the Charniak and Collins parsers being lexicalized compared to parent annotation and state splitting and the like, which is more along the lines of these latent variable models. And this allows this transition also, or this allows us to explore this transition from minimal to composed by principally incorporating context and using latent variable models instead of, say, arbitrarily taking rules and composing them to generate larger rules. So just a brief aside, what do I exactly mean by minimal grammars and how am I extracting them? So in this particular case, we use an algorithm from previous work, which I won't get into the details of, but the basic idea is we can extract much smaller grammars and we encode context not through larger translation rules, but we actually encode context through the latent variables and the latent states, and I'll discuss how we do that through these latent synchronous context-free grammars. These grammars are small, so we don't need to do any pruning during decoding. And as I mentioned before, we're going to restrict ourselves to single category X grammars, in other words, the classic Hiero grammars of David Chang from 2005/2007. So let's go back to this example more concretely, and I'll tell you exactly what I mean here. So in this particular case, we can come up with a minimal derivation, a synchronous derivation tree. And over here, the ambiguity is basically with these particular rules. So Fragen can translate to questions or ask. And so the basic idea now is we can augment every non-terminal in our tree with a latent state. In this particular case, let's assume the latent states, we have two latent states. And the basic idea is that these latent state configurations, so H1 and H2, reflect certain preferences for types of context as reflected by inside tree combinations and outside tree combinations. And so the idea is that with this latent variable model, once we do inside-outside parsing, or once we marginalize, we will basically have, in the first instance, we would prefer Fragen to translate to questions, and we would ideally not like Fragen to translate to ask because of the context in which it occurs in terms of the tree. And in the second instance, we would prefer the opposite sense. So the basic idea of this work is to start off with this minimal grammar and incorporate the context through a latent variable model instead of stuffing that information to generate larger translation rules. This necessitates a generalization of the inside-outside algorithm to a tensor version, which I'll first discuss. And then we present two methods to estimate parameters of this model, one using EM, or expectation maximization, and the other using the method of moments, which I will also call the spectral method as well, so I'll use those terms interchangeably. And the one result, if you don't remember anything from this talk, the one result I'd like you to remember, though, is that a minimal grammar in combination with a latent variable model and a particular estimation technique, the method of moments estimation, is roughly as good as, if not slightly better than, the traditional hierarchical grammar. But obviously, because we're using a minimal grammar, the grammars are much smaller. So first, let me discuss inference, and with this method, you'll kind of, after discussing inference, you'll be able to see how the latent CFG model works in some level. So this is, first of all, a generalization of some previous work in latent PCFGs. This isn't the standard way of kind of describing latent PCFGs, but in terms of these tensors and matrices, which I'll discuss, but it makes it easier for the spectral method, as we'll see later. So the basic idea is that we want to attach a parameter to every translation rule in our corpus. So for example, for binary translation rules, we'll have a tensor. For unary rules, we'll have matrices and the like. And so the non-terminals on the right-hand side are aligned as in synchronous grammars, and so are the latent variables. So basically, the preferences for certain inside-outside tree combinations are reflected in the values in these parameters. So let's see how we can do inference here. So standard regular inside-outside algorithm, what we do is we take we basically multiply the scale, we essentially do a scalar multiplication. Psi r is the potential for rule r, and then we multiply the alphas, which correspond to the inside probability terms, in this case the inside calculation, by that scalar. And essentially, the alphas here represent scalar posteriors of x spanning the span ij. So we'll see over here in that CKY chart, the marginal for cell ij might not be as preferred, for example, as the marginal for cell pq. And now for the tensor formulation of the inside-outside algorithm, it's essentially the same thing, except we generalize the scalar multiplication. We're essentially doing a matrix multiplication. So we're doing what is known as a tensor contraction. So if I multiply a matrix, if I multiply a tensor by a vector, I'll get a matrix out. And so the basic idea over here is that along the second mode, corresponding to the second child of that particular non-terminal x1, we're essentially going to multiply a vector that represents the alpha term along that second mode. So we're going to fix everything else in the tensor and multiply along that. And by that, we're marginalizing over the latent states. The intuition is actually fairly similar from matrix multiplication, as you can see here. So matrix multiplication on the right is essentially multiplication of the first mode of this two-way tensor, which is essentially a matrix. And then so what we can see here basically is that in each cell, instead of having a scalar that represents the marginal of that cell, we'll actually have a vector. And each element of that vector will represent how likely that latent state is, or the score of that latent state. So it's essentially a generalization of these scalars to these vectors you can think of. And correspondingly, we can do the same with the outside calculations. All right, so now that we've kind of described the model, latent as CFGs, and we've seen how we can do marginalize with this model, let's figure out how we can estimate those parameters, those tensors, those matrices, and those vectors. So I'll discuss two methods of estimation. One is the EM way. So over here, what we'd like to do is we'd like to learn the latent state parameters that maximize likelihood. And so the first thing we'll do is we'll use our current parameters, and we'll do a constrained decoding of the sentence pairs that we have in our corpus, and using the decoding algorithm that I presented before. And what we'll obtain is partial counts over these latent states. So for example, for every non-terminal, we'll have the outside probability vector, which represents these partial counts, and the inside vectors. Then what we need to do, and intuitively these partial counts kind of represent the m-dimensional representations of these contexts, these inside and outside contexts in the latent space. So what we need to do is convert those representations into translation rules, or in other words, represent translation rules in terms of the low-dimensional context. And we do that by computing these outer products. So I'm computing the correlations in this m-dimensional space, taking those inside and outside vectors and doing outer products. We can do the same with unary and pre-terminal rules. And then in the m step, we do an overall normalization. So I also wanted to give, first of all, an intuition as to how the method of moments estimation method works, and then I'll talk about some details in the following slides. The first question is, what are we projecting from and to? So let's make this more concrete. We have the following translation rule in the corpus, and this might occur in a bunch of different settings. Here are two different settings amongst many in which this translation rule occurs. So what we can do is we can then define features of the inside trees and features of the outside trees, and we have these feature vectors. We can compute the outer product of these feature vectors, and we'll get an empirical covariance matrix of how the inside features vary with the outside features. And then we can decompose that using a singular value decomposition. So the basic idea here is we're expressing translation rules, in this case Verdenin X1 Larsen, in terms of inside and outside features. We then project those features into this lower dimensional space using linear algebra techniques, and then we do all of our work, subsequent work in that space. So let's make this a little bit more precise. In the first step, we want to do feature extraction, and say in this particular case, we have the rule X3, or the non-terminal X3, and what we can do is we can extract features from the inside trees of that terminal, non-terminal. We can extract features also from the outside trees. Inside, features can include things like rule indicator features. In this particular case, just the regular kind of monotonic glue rule, that's what it's called in Hiero. We can also extract features of the children nodes, so rule indicator features of the child rules, lexical features as well, and the corresponding thing can also be done on the outside trees too. Then the next thing is, once we have those features, we then take an outer product of those features, so we see how those features covary with each other. We compute the singular value decomposition, and then we have these projection matrices, and we have these lower dimensional representations now of inside features phi, so what we'll call y here, and outside features psi. And note that this is the main difference actually between the EM estimation method and our estimation method here. In EM, what we did is we had our current states, we had our current current parameters rather, and we use those current parameters to obtain partial counts, and those partial counts correspond to y and z. Over here, what we've done is the one-shot estimation method. We've essentially computed or expressed our translation rules in terms of inside-outside features, computed a singular value decomposition, and then that's it. After that, though, it's practically the same, modulo a few things like normalization constants and the like. How do we convert those lower dimensional representations of inside and outside features into lower dimensional representations of translation rules as defined by those inside and outside contexts? And so what we do is the same thing. We take outer products for binary rules, tensors, For unary rules, matrices, and for pre-terminal rules, we use just regular vectors. And so that's essentially the estimation techniques that we're looking at here. So just to summarize what we've done, we've looked at a generalization of latent PCFGs to latent SCFGs, so basically a latent variable model to take into account the context. We've seen how to do inference using this model, and we've also seen 2 different ways of estimating parameters for this model. So now I'll briefly talk about some experiments. In terms of evaluation, we looked at the BTech Chinese English corpus, and the baselines we looked at is the standard Hiero system baseline. So this is, as I referred to earlier in the talk, a composed grammar where we kind of have fairly large translation rules, and on average, we found that these grammars were about 20 to 40 times larger than the minimal grammars. We also had a corresponding minimal grammar baseline, so the exact same features as the standard Hiero system, except just with a much smaller grammar. And we had a maximum likelihood estimate, basically baseline, which is fairly similar to the minimal grammar, with a few differences in terms of the features, which you can look at in the paper. And then the features that I described before, rule indicator, lexical features, and length features, are essentially the ones that are used. In terms of how we integrate basically the latent variable model into the standard MT pipeline, we use the tensor formulation of the inside-outside algorithm that I presented before to compute rule marginals, so the marginals for every rule. Now these marginals are interesting because they're joint source target marginals, so they're conditioned on the left-hand side of the rule. And so what we can do is we can then make them conditional upon the source, so basically just sum over all, so normalize by summing over all occurrences of the source phrase, and we can also do the reverse as well, condition on the target. And then in terms of how exactly we integrated it with the MT tuning setups, I'll refer you to the paper for those details. All right, so now let's look at some results on the test set. The dev set results are extremely similar, so I'm excluding them. The first thing over here is the baselines. So we see, first of all, this composed minimal gap, which is fairly standard and which has been previously observed in the literature, of about, I would say, it's almost like 3 blue points over here. And this is somewhat observed and somewhat expected. Then there's like I said, there's a slight variation in the 2 baselines that we have, the MLE baseline and the minimal grammar baseline, but they're practically the same. Now, as we start kind of doing, I'll first present the spectral results of the method of moments estimator results. And as we start off with m equals 1, we get roughly the same performance as the minimal grammar, which makes sense. I mean, we're not really doing any latent state modeling or latent variable modeling here if it's just one latent state. As we increase latent state, so this is m equals 8, we get a little bit of a better performance. And we find that performance peaks at m equals 16. So this is 16 latent states using rule indicator features only. And we actually find that the performance is as good as the hierogrammer, actually slightly better than the hierogrammer. But instead of incorporating context, like I said, into these large translation models, we're taking this into account using the latent variables. We added some additional features as well, looked at lexical features and smoothing and length features and whatnot, and we found that didn't help so much, primarily because I think a lot of this information is already encapsulated in the rule indicator features. And then as we added more rank, we essentially got more noise and we didn't get better performance. We got much worse performance actually, which shows that at least in this particular setting, m equals 16 states is somewhat ideal. Now for the EM experiments, we also found a very similar trend. The peak is at m equals 16. The interesting thing here, and then you'll notice these error bars because EM is susceptible to local minima and the like, so we had to run this a bunch of times. But you'll notice also that EM is not as strong in this sense as the spectral estimator. And this is a slightly surprising result considering previous work that shows that they're pretty much equivalent. And so we have a few reasons for this. One is maybe the local minima issue. The other one also is maybe the EM comparison is not as fair, so we aren't featurizing EM. You can do a Burkirk-Patrick style EM style featurization. There are a couple of other reasons, and we're looking into this, but it's interesting to see that this gap compared to the spectral case. Now, I just wanted to touch a little bit on some analysis to try to figure out what exactly is going on here. So these, I've basically compared the three different estimators, maximum likelihood, which is similar to the minimal grammar case, and then the two latent variable models. So what we can see here, and I don't know Chinese, but I think this is a classic example of like the zero pronoun effect. I think the object has been dropped here, and that kind of screws up the translation for the MLE. You can see, and so let me just also describe what these colors are. So these are CKY heat charts. Blue is higher, basically, so a higher marginal, higher posterior probability is blue, and red is a lower posterior probability after performing CKY inference. And you'll see over here that the subject, so the object which has been dropped is fairly unlikely to be in the subject span in the MLE case, but in the EM and method of moments, we see that from that top level row or that top level rule that the marginals are much higher. EM, though, is very interesting because it kind of uniformly assigns, I mean, it's all those marginals are uniformly high, whereas in the method of moments case, we can actually distinguish between different spans, and we can actually prefer one span to another. So just to summarize, the basic idea that we presented here is to start off with a minimal grammar and incorporate context not by adding more contextual or local context information inside the translation rules, but rather by incorporating it through a latent variable model. This necessitated a reformulation of the inside-outside algorithm to a tensor version, where we're essentially just marginalizing over latent states. So we do dot products or matrix multiplications instead of scalar multiplications. We presented two different parameter estimation techniques, one based on likelihood maximization and one based on the method of moments. And the result I'd like you to once again keep in mind is that a minimal grammar, which is much smaller than the standard hierogrammar, in combination with a latent variable model and the method of moments estimator, is pretty much as good as, if not slightly better than, the standard hierogrammar that we're all fairly used to. And with that, I'd like to thank you, and the code is all available online, so you can run this on your parallel data sets and see how it does. Thank you.
2 minutes for questions. So, anybody? Questions? Yes, go ahead.
Thank you. This is very interesting work. I had two questions. The first is, did you try this on any larger data sets?
We did. We have tried it on some larger data sets. The results were, it was interesting because I think the main limitation for me is the statistical estimation issue. So one thing about method of moments estimators is they're not as necessarily efficient statistically. And so basically the main issue with a lot of the larger data sets, and something that we're kind of grappling with, is you have a much longer tail compared to, say, monolingual parsing. And that kind of, it has some variable or mixed results. But we're still kind of working on that aspect as well. So also, I think that my implementation is not as scalable as it can be. So we've also had some computational concerns, so I might re-implement some of the stuff. So.
Okay, thank you. And the second question was, you mentioned that you're not doing pruning. And just to confirm, you're not removing any rules from your model.
Right, I'm not removing any rules or doing any beam search or anything like that in the decoding step, exactly.
So how can you not do beam search if you're incorporating a language model?
Okay, yeah, fair enough. Okay, yeah, in that sense, yes. But I'm not pruning the model. Sorry, I misspoke when I meant beam search. I'm not pruning the model in terms of model sizes and so on.
Okay,
yes.
Thank you.
Hi. Did you also prune the hierogrammar? Because if you don't prune it, of course it will be large, but usually it makes sense to discard singleton hierarchical rules. Maybe you could try to bring it down to the same size and measure translation quality then?
I did. Actually, the hierogrammar we looked at a bunch of different variants of the hierogrammar. We looked at the full-size hierogrammar. We looked at pruning singletons. We also looked at kind of sorting based on forward phrasal probabilities, E given F, and took the top 15 translation rules. And actually, so I took the best of all of those configurations. So the best result is a pruned hierogrammar in that sense, where we kind of took the all the rules, sorted them by probability of E given F, and took the top 15 basically. So it is a pruned variant, yes.
Okay, so let's thank Avneesh again.